In this video, we're going to learn about buffers. We're going to learn how to prepare buffers. You have heard the word buffer before. You know that a buffer in the context of a titration is a solution in which there exists the acid and its conjugate base in the same solution with similar concentrations, not necessarily 50-50, but on this end it would be 730 and on this end it would be 37, right? And here halfway it's 50-50. And we have learned that in that solution additions of, in this case, base change the pH not too much, okay? And that characteristic of a buffer solution is very relevant when it comes to biological systems, because biological systems work at a fairly narrow range of pH. It's important that we keep the pH, or the biological systems keep the pH at a constant pH, because a large jump of pH would denaturalize the proteins, would make the enzymes not work, and that would result in death. Okay, so a system of a buffer that is very common in biological systems is the carbonate, the carbonic acid carbonate. So in a specific range of pH, pretty much around here, where there is a combination of carbonic acid with hydrogen carbonate, the biological systems will use this buffer to keep the pH around 7. Notice that the pH of human blood is 7.4. A change of unit of point of 0.4 units of pH will result in death. So this is how important it is to have a strong buffer system in any living system. So as I said, the objective of that buffer is to keep the pH more or less constant. All right. The characteristics of a buffer is that it will, as we said, it will lessen the impact of the pH. Its characteristic also is that it has similar concentration of the acid and the conjugate base. In this case, the acid would be carbonic acid and the conjugate base is hydrogen carbonate. And it will have its maximum capacity to absorb the changes in pH when there is a 50-50 distribution of both. Of course, all buffers have a limit, and when you consume one, either the acid or its conjugate base, you will say that you destroy the buffer. Okay. What we're going to do now is to understand how we can prepare buffers in a lab, or what kind of reactions lead to the formation of a buffer. Okay. So these are the questions. All right. Identify which of the following solutions will make a buffer. And in the case that it makes a buffer, calculate the proximate pH. Note that you could not calculate the pH in the case when it's not a buffer, but in this case we're just going to calculate when it forms a buffer. Alright, in this case we're mixing ammonia and sodium hydroxide. Notice though that this is a base and this is also a base. Therefore, when you mix ammonia and OH negative, this will not lead to any reaction. Please do not think that with NaOH you can form, with hydroxide you can form this ion. This is very basic, it's never formed. Therefore, the combination of these two will not form a buffer. It would form a buffer if, for example, we could add some acid, but if we're adding base, therefore it will not form a buffer. You will see in the next example. If we're mixing sodium dihydrogen phosphate with hydrochloric acid, well, we know that dihydrogen phosphate reacts with the strong acid to form phosphoric acid. Okay? Or if you prefer, it depends how you want to draw the proton. Okay? Now, have we added too much of the acid to just have phosphoric acid? Let's see. How many moles is this? Well, the number of moles, as you know, is volume times molarity. So 0.01 liter times 2 molar. This is 2 times 10 to the negative 3. So I have 2 times 10 to the negative 3 moles of dihydrogen phosphate. How many moles of hydrochloric acid or hydronium do I have? From here I get that I have 0.01 liters times 0.1. This is times to the negative 3. Notice that initially this is my limiting reagent, so at the end this is all gone. What it's left is 10 to the negative 3, and all that it's gone now, it appears here as 10 to the negative 3. So I have a buffer in its maximum of this capacity, which is when I have equal amounts of the acid and its conjugate base. All right, and the pH of this solution is pH equal to pKa log of concentration of base, concentration of acid. This is 10 to the negative 3 moles divided by the volume. 10 to the negative 3 moles divided by the volume. Notice volume and volume disappears. Actually, this is 1. Logarithm of 1 is 0. pH is equal to pKa. What pKa are we referring to? We will refer to the pKa that connects these two species, which is the first pKa. It's the most acidic one, that is this one. So pH is equal to pKa, the first pKa. That's the pH resulting when you mix these two species in these concentrations and volumes. Let's keep going. Now notice that we're going to do the same, but now we're going to be adding base. Alright, so we have the hydrogen phosphate and base, and that will give hydrogen phosphate and water. Okay, from here, from previously, we said that we had 2 times 10 to the negative 3, so we have 2 times 10 to the negative 3 moles, and from here we said that we have 10 to the negative 3 moles of base. Again, we are in a very similar situation. 2 times 10 to the negative 3, and this is 10 to the negative 3 initially. So at the end, I will have this all gone, just 10 to the negative 3 left, and the rest will be converted into its conjugate base. So notice what was the conjugate base, now it's the acid. So because this is a multiprotic acid, the pH again will be equal to the pKa, because again, log of the concentration of base over concentration of acid will cancel, the volume cancels out. This is equal to 1, logarithm of 1 is 0. However, notice that the pKa now is the one that connects these two species. This is the second pKa, and the second pKa here is 7.198. So the pH will be 7.198. Alright? Now let's keep going. In this case, we're mixing nitric acid and potassium hydroxide. Nitric acid and potassium hydroxide, well, they just give potassium, nitrate, and water. Even if we could spend some time here. This is 10 to the negative 3, and this is 5 times 10 to the negative 4 moles. I'm going a little fast here, but notice that none of these are weak acids or weak bases, so no buffer for you. If it's not a weak acid and it's conjugate weak base, you will not be able to form a buffer. That's important to understand, because with exclusively strong acids you cannot form a buffer. Alright? And finally, let's study this one. Notice that now what we're adding is acetic acid and its conjugate acetate, the conjugate base. These two do not react with each other. So what you actually have is just the perfect buffer. Not necessarily the perfect buffer, but even though you don't have any reaction, by adding these two in solution, because they do not react with each other, they already form a buffer. Alright, so now let's see what is the pH. Well, the pH will be equal to the pKa, and we should look up what pKa is of the acetic acid. I finally have memorized it. It's 4.5. Logarithm of concentration of acetate over concentration of acetic acid. So first, the answer is yes, this will form a buffer. 2, what is its pH? Well, the total volume will be 15 milliliters, or if you will, 0.015 liters. Okay, but notice that we will not, typically we don't need to bother with the volume, we just need to calculate the number of moles. Log. So, how many moles of acetate do I have? 5 milliliters, so from this, 5 milliliters at 0.1 molar, this is 0.005 liters times 0.1, this is 5 times 10 to the negative 4, 5 times 10 to the negative 4, you will see that the volume cancels out, and from here, this is 0.01 liter times 0.1, this is 10 to the negative 3. This is 10 to the negative 3 divided by volume. Alright, notice that this numerator is smaller than the denominator. This ratio will be smaller than 1. The logarithm of something smaller than 1 is negative, so you know that the pH will be a little bit lower than 4.5, which makes sense. Makes sense because you have more acid than base. If you have more acid than base, actually twice as much, expect the pH to be a little bit more acid than when you have a 50-50 distribution. Hopefully this makes sense. Take-home messages: there's different ways of making a buffer. One is adding directly the acid and its conjugate base. The other one is adding an acid and a strong base, so a weak acid with a strong base, or the other one is adding a weak base with strong acid. Hopefully that makes some sense. We'll keep practicing more.